There is an adage that goes as assumption is the mother of all muck-ups. Well, though generally speaking this may be true, however, specifically in the case of linear regression, it is the assumptions that make or break linear regression. Let us find out how. Welcome back to yet another video from Learning Puri, a channel for applied learning. Here you get tutorials and tips on a variety of topics, and this one is no exception.
In the earlier video, I had mentioned that we will deal with assumptions that need to be satisfied for a successful linear regression in part 2 of the video. So here we are in this second part as a continuation to the earlier tutorial. So hold on to your hats because we are not just talking about the basics. We are exploring the assumptions of linear regression. Those sneaky little criteria that can make or break your predictive model. So buckle up and get ready for a wild ride through the world of assumptions. Before we jump onto the list of assumptions, let us do a quick recap on linear regression. In a nutshell, linear regression is a statistical method used to model the relationship between a dependent variable and one or more independent variables. We use linear regression to make predictions about unseen data. Pretty cool, right? Now, you might be wondering, why do we even care about assumptions? Well, assumptions are the foundation of any statistical model. They ensure that the model is valid and produces correct results. If your assumptions are violated, it is like building a house on shaky foundation. It is only a matter of time before it all comes crashing down. So let's roll up our sleeves and take a closer look at the assumptions of linear regression. The 5 assumptions are as follows. A. The relationship between independent variables and dependent variable is linear. B. There are no hidden relationships between variables. In other words, there is no autocorrelation between the different values of residual. C. Error term or the residuals follow a normal distribution. D. The size of error does not change significantly across the values of the independent variable. And E. No significant outliers in the dataset. The first assumption of linear regression is linearity. It states that the relationship between the dependent and independent variables should be linear. To check this assumption, we can create a scatter plot of the variables and look for a clear, straight line trend. If the relationship looks more like a roller coaster rather than a straight line, we need to consider a different model or transform the variables to achieve linearity. However, in our model, it was not the case, and we satisfied the first assumption. Next up in line is the assumption of independence, which requires that the observations in your dataset are independent of each other. In other words, the absence of autocorrelation. This means that the value of one observation should not be influenced by the value of another observation. We can employ 2 methods to check for autocorrelation. In the first method, we can look for patterns or trends in the residuals, that is, the difference between the observed and the predicted values, compared with the regressor, that is, the discount percentage. If you notice any autocorrelation or clustering in the residuals, it is a red flag that independence might be violated. However, in this case, there is neither any trend nor the correlation coefficient indicates any linearity. The plot exhibits a random scatter. Just in case anyone has doubts about the randomness, we could also use the Durbin-Watson statistic to reconfirm this finding from the scatter plot. To use the DW statistic, we start with the null hypothesis that no autocorrelation exists in the data. We will use the value of residuals that we have obtained to calculate the DW statistic. We use the following formula for the DW statistic to obtain the value like so. The calculated DW statistic is then compared with the DW statistic seen in the DW table. The following is a small extract from the DW statistic table. In our model, we have only one regressor and the number of observations is 11. Furthermore, we are testing the hypothesis at a significance level of 5%. Hence, we compare the calculated value with the values in the row for sample size 11. If the calculated value is greater than the upper bound, we do not reject the null hypothesis. We do not reject the null hypothesis even when the calculated value is between the lower and the upper bounds. Since, in our case, the calculated DW statistic value is greater than the upper bound, we do not reject the null hypothesis. We, therefore, conclude that there is no autocorrelation in the dataset. To gain a complete understanding of calculation and interpretation of DW statistic, we will need a separate tutorial. The DW statistic calls for a separate treatment. Hence, we will avoid any further details about it in this tutorial. So far, so good. We have satisfied the second assumption. So, let's move ahead to test if errors are normally distributed. This assumption states that the errors in the regression model should be normally distributed. In other words, the errors should follow a bell-shaped curve. If the errors are not normally distributed, it can affect the accuracy of the model and lead to incorrect predictions. So do not let normality be the elephant in the room. We make sure to check it by assessing normality using visual inspections such as QQ or quantile plots. We can also use statistical tests like the Shapiro-Wilk test along with the QQ plots. However, the Shapiro-Wilk test requires a separate discussion. For a QQ plot, we could either use the residuals versus sample percentiles plot, or we could use the figures of the sales in thousands and calculate sample percentiles for the data as in this table. The regression analysis available in Excel also creates this plot as a normal probability plot like so. In the plot, we observe that the data is linear. The observation is corroborated by the near 1 value of the Pearson's correlation coefficient. With this, we have ticked one more assumption of our list. Let us now examine the fourth assumption on our list, which is homoscedasticity. This fancy term, homoscedasticity, simply means that the variance of the errors in the regression model should be constant across all levels of independent variables. If the errors have different variances, it is like trying to fit a square peg into a round hole. It just won't work. In other words, the spread of the residuals should be the same no matter where you are on the scatter plot. To check for homoscedasticity, you can plot the residuals against the predicted values and look for a consistent spread. If you see a funnel shape or any other pattern, it is a sign that homoscedasticity might be violated. In this data set, when we plot the residuals versus the fitted or predicted values, we do not see any pattern. Therefore, we can safely say that homoscedasticity is not violated. Now, for those who felt a little uncomfortable trying to interpret the chart, there is a statistical test by the name Buse-Pagan test, which is also available to test for homoscedasticity. The test uses the null hypothesis that homoscedasticity is present. It is based on chi-square distribution. I've already run the chi-square test statistic, which yields the value 0.3848. The value of chi-square statistic is compared with an alpha value of 0.05, which is the level of significance. If the chi-square test statistic value is greater than 0.05, then we do not reject the null hypothesis. So rest assured that our conclusion based on the chart seen earlier holds very well. Again, the Buse-Pagan test calls for a separate tutorial for doing justice to it. Hence, we will not discuss any details of the test in this tutorial. Finally, we come to the fifth and the last assumption, that is, no significant outliers. Most often, this is not an assumption that gets discussed. It is assumed to be true when linear regression is run on a dataset. However, this is a critical assumption that should not be ignored and requires some deliberation. There are two types of outliers. The first one, where the data point is way out of line, and the second type, where the data point is an extreme value but still may be a part of the model. In the first case, we may have to take a call to remove the data point completely. However, in the second case, we could allow the data point to be a part of the model. However, these decisions are taken post sufficient exploratory analysis and investigation on the dataset. For the dataset we were working with, we did not have any significant outlier. Therefore, our fifth and final assumption too is satisfied. Alrighty then. If you think we are done, then hold on. There is still work in progress. Let us travel back in time to part 1 of this tutorial. We will revisit the 5 steps from part 1 of this tutorial where we learned to conduct linear regression. For those who have watched the earlier video, you will remember that we had completed the first 3 steps of simple linear regression. We completed the 4th step when we satisfied all the assumptions for conducting linear regression in this tutorial. With this stage completion, it means that the linear regression model we have obtained holds good for the data. Therefore, we can now use the same equation to make predictions on fictional data. To refresh your memory, remember that Y is the predicted sales and X is the percentage discount offered. So, for a discount of 13.5%, we can safely predict a sale of approximately 53.38 thousand units. A point to remember is that the prediction will be valid only within the range of the data for which the regression model was run. That is, for any value of percentage discounts running from 11.5% to 16%.
Well, before all of you erupt into an argument on the prediction capability of the model, let me remind you to first subscribe to the channel and do all the YouTube relevant things. Do not forget to share the link for this video with your friends. Let them benefit as well. Okay, coming back to the point. Linear regression is a prediction model and not a forecasting model. Our original data set had percentage discount values ranging from 11.5% to 16%. A prediction model is effective for any value only within this range. If anyone is interested in any value beyond the range of the dataset, we use forecasting techniques and not predictive techniques. Well, that being said, stay healthy and stay peaceful till we meet in the next video. Thanks for watching.